Now that I've solved a little bit about the ammonia molecule, let's keep in mind that what I want to get to is very large molecules. So I want to keep pushing the envelope on molecules so that I can see where the boundaries are. And when I hit those boundaries, there's another interesting thing we can do is use different techniques so that it doesn't kill the memory or so that I'm not out of memory. Because when I ran one of the molecules, it ran out of memory at about 29 gigabytes, and it hadn't even got to the point where it could report the qubits. So it failed really early. So that caused another little problem that I want to investigate. Okay, these show the results of a refactoring of the program so that I could handle more molecules. So what I did was I added to the list hydrogen, and you can see hydrogen, the whole thing only takes about 8 seconds to run, 7 or 8 seconds to run the thing. And even at the highest basis, it's only consuming about 279 megabytes, which is not much. Then we go down to ammonia, which I've already talked about, and notice that it's consuming 6 gigabytes now. And on an earlier one, it consumed only 4 gigabytes. So this might have had something to do with the refactoring. Go on to CH4. And CH4, you notice I'm using 4 gigabytes, and I haven't even hit this ceiling. I've got the molecule done. This is STO3G. Here I use 0.33 gigabytes after finished building the Hamiltonian. Finish the molecule. It takes up 0.33 gigabytes. That's not really much difference. And 1.0 gigabytes. Let's go down to 6-31G. Here I'm using, the molecule took 1.15 gigabytes. That's starting to mean something. And let's just go ahead down to this last one, 44 qubits. And I'm using memory of 3.48 gigabytes. What does that tell us? Well, it tells us that we need more information. And on the CH4, we actually have another result that I came up with, was that I found when it does this thing called mapping, it never completes the mapping. So somewhere in the mapping, it blows up. So that's my next stage of investigation. As I continued the investigation, I found out that the mapping time is a separate element. Not just do the execution time, but include the time for the molecule build, the time for the Hamiltonian build, which the expensive part of it, or time expensive and memory expensive, is coming up with these things called the Pauli terms. So those Pauli terms take a long time to develop before we even talk about the energy. So what I've done is actually break it down into a different experiment. There's an experiment that just looks at the molecule build and mapping along with peak memory usage, and I actually did get the CH4 to run correctly. I just found out that you can't have many other applications going that will steal from the memory. So as we go forward with this, I started to find out that the architecture was wrong. So I started developing a new architecture, and as I was making these major changes to the code, I thought, I need to find out what's going on with this so that I can back up if I make a mistake in all these code changes. So I now developed a backup server on my second lower memory machine, and that is a headless server, meaning that it doesn't have a keyboard or a monitor, but just communicates through the system that has the larger memory, the faster execution time, and all those variables that help me do the quantum chemistry. So as I go forward with this, what I'm finding is that I have to use a version control system. Even though when I was a software engineer, I used version control systems where you check out and check in files, I started to discover that Git was much better. Git was developed by the same guy that developed Linux, and it's a beautiful thing. And with Git, I also have the version control I need. I do these things called commits, which will show what changes have been made since the previous commit. And I can do a git push, which will put all this code on the backup server in a very compressed manner. So this is really a valuable tool that I've discovered. And now my work has changed a lot. Now I'm finding out that I'm spending more time designing the quantum chemistry framework rather than just do one experiment at a time. So this new quantum chemistry framework will allow me to break everything up into separate experiments. And those experiments can be scaling with mapping, the scaling with all these different bases with mapping plus energy, which when I went to do the mapping plus energy, I'm finding out that the code doesn't even calculate energy properly. The energy is just a representation value or a guess to start the whole ball rolling, but never involving the molecule and chemistry. And in the process of that, I'm finding out that I have to figure out what kind of solver I'm going to use, because there's different choices of solvers. When I have the thing called this experiment class, everything in that experiment is broken out into various choices that I can make. In the experiment class, we have experiment type, the experiment's molecule, the experiment's basis, and the experiment mapping type. Yes, there's more than one way that you can do the mapping. And then the solver, which is whether you're using an exact solver or other estimated solvers for the energy. So in the next video, I'm going to start explaining the architecture and the structure of what I'm doing, so I can review my work and find maybe flaws or pieces that need to be added to it.